Hello friends, welcome to the next video lecture as far as our heat transfer course is concerned. In the last lecture what we have discussed why that negative sign is added as far as Fourier's law of heat conduction is concerned. In today's lecture we are going to discuss very important point, that is nothing but how we can make use of electrical analogy while solving the problems as far as the flat plates are concerned, or composite walls are concerned, or composite cylinders are concerned, or composite spheres are concerned. In order to solve or in order to understand the problems regarding that, what we are going to do, we are going to deduce these thermal circuits in terms of electrical circuits, and for that this electrical analogy plays very important role. Before understanding that electrical analogy, let us consider a plane wall, okay, which is having two surfaces. First surface is at temperature T1 and second surface is at temperature T2, having thickness L. And here specifically we have considered this T1 is greater than T2. That's why heat will start flowing from this surface which is at temperature T1 towards the surface which is at a temperature T2. Now, from Fourier's law of heat conduction, what we can write, Q is equal to K into dt upon dx, and here I have to consider the negative sign. Okay. After further simplification, what I can write, Q into dx is equal to minus K into A into dt. Now, this equation which we have written, how we have written that equation? Out of these complete plane wall, I have considered a small volume element. This small volume element I have considered, and I have written this equation. Now, if I have to calculate the total amount of heat transferred from this surface toward this surface, then how we can calculate it? Simply we have to integrate this equation number A between the limits. Here the value of x is here 0, and at this location x is equal to L. Okay, or we can say at x is equal to 0 temperature is T1, and at x is equal to L temperature is equal to T2. Now, in order to calculate the total heat transfer throughout this plane wall, what we have to do, we have to integrate equation number A. Now, what I will get as a result of integration, okay, minus K into A integration dt. Okay, and here we have to use the limits of integration. Here x is equal to 0 and x is equal to L. Here at x is equal to 0 temperature is T1, and at x is equal to L temperature is T2. Go on simplifying, what I will get here, Q into integration of dx is x, okay, between the limits 0 to L. Okay, here as it is negative sign, minus K into A integration of dt is t between the limits T1 to T2. Go on simplifying, here higher limit minus lower limit, Q into bracket L minus 0 is equal to minus K into A higher limit T2 minus T1. Okay. Now just multiply this negative sign inside the bracket, what I will get, Q into L is equal to K into A into bracket T1 minus T2. Go on further simplification, what I will get, I can write Q is equal to T1 minus T2 divided by L upon KA. Okay, here I have written this KA as denominator of denominator, hence it is numerator only. Okay, let us call this as an equation number B, or we can have further simplification, delta T divided by L upon KA. Let us call this as equation number C. Now make use of the electrical analogy. According to Ohm's law, what we are doing? I is equal to dV upon RE. What is this I? I is nothing but electric current, dV is potential difference, and RE is nothing but what? Electrical resistance. Now let us call this as equation number D. Now let us compare this equation number D and equation number C. यहाँ पे जो भी हमने प्रिपेयर किया है प्लेन वॉल, उसके थ्रू क्या फ्लो होता है? हीट फ्लो होता है. और यहाँ पे हमने जो भी इलेक्ट्रिक सर्किट प्रिपेयर किया है इसके थ्रू क्या फ्लो होता है, करंट फ्लो होता है, और वी कैन से इट एज ए I. Here this material will offer some resistance, okay, and until and unless there is a potential difference, okay, यहाँ पे इलेक्ट्रिक करंट फ्लो होगा क्या? हाँ, अगर ये पोटेंशियल डिफरेंस ही नहीं रहेगा तो देयर इज नो क्वेश्चन ऑफ फ्लो ऑफ दिस इलेक्ट्रिक करंट. Okay. Similarly, for this plane wall, by comparing it with electrical circuit, we can prepare the thermal circuit. Now see how we can prepare. Let us take the analogy. Okay, the electric current I, we can say it as, just compare these two equations. This I is analogous to heat transfer through that plane wall, or we can say it as a thermal circuit. Here as electric current was flowing, we were calling it as an electric circuit. Here as heat is flowing through this plane wall or through this circuit, we are calling it as a thermal circuit. Then potential difference is analogous to, potential difference कहाँ पे है? यहाँ पे है. यहाँ पे क्या है? Potential difference is analogous to temperature difference. And finally, electrical resistance is analogous to, here we will call it as a thermal resistance, and as far as plane walls are concerned, that value is L upon Ka. Okay. Now I will repeat it once again. This electric current is analogous to heat transfer through that thermal circuit. Then potential difference is analogous to temperature difference, and electrical resistance is analogous to thermal resistance. Here, as far as electric circuits are concerned, the driving force is nothing but what? Driving force is your potential difference. Okay, and as far as these thermal circuits are concerned, that driving force is nothing but what? Temperature difference. यहाँ पे अगर ये temperature difference ही नहीं होगा, then there is no question of transfer of heat. Okay, now let us prepare the equivalent thermal circuit as just now we have studied the electric analogy. Here temperature कितना है? T1, here temperature T2. Through that circuit, Q amount of heat is flowing, and the resistance offered by this material is nothing but what? RTH. And as far as these plane walls are concerned, that value is nothing but what? L upon Ka. I think so you might be clear how we can make use of this electrical analogy and how we can prepare the equivalent thermal circuits. Now let us assume that here we have considered one resistance only. Now like that, suppose two resistors are connected in a series. Let us say it as a R1 and R2. As far as that electric circuits are concerned, how I am going to simplify it? The equivalent of these two resistances is nothing but what? R1 plus R2. Let us assume that two walls are there which are connected in series. Okay, here how we can prepare the thermal circuit? These are nothing but two resistances. Let us say it as a RTH1 and here RTH2. In this case, how we are going to calculate the equivalent thermal resistance? That is equal to, by comparing it with the series connection, what we can write here? RTH1 plus RTH2. Depending upon whether it is a plane wall or whether it is a cylinder or whether it is a sphere, this values generally just now we have derived that RTH as per as plane walls are concerned, that value is L upon Ka. Okay, if I will replace this plane wall with the cylinder, then this value might come different. If I will replace it with the sphere, then also this value may come different. Okay, in further lectures what we are going to do, we are going to derive these equations. I think so you might be clear how we can prepare the thermal circuits which are analogous to electrical circuits, and how we are going to use these series connection and parallel connections in case of our composite walls, cylinders or spheres. Okay, that's it as far as today's video lecture is concerned. In next video lecture we are going to prepare general heat conduction equation as per as our Cartesian coordinates are concerned.